So far, we've already done the spring. Dealt with the problem with the spring, with a rope or cable. And we did one problem that involved a tank full of water. But we still should look at some other scenarios. The problems in the tank that do involve water. Just different tanks. The one we did before was a circular cylinder, right? It was a circular cylinder. So I thought I'd start with this is one like number 19 on page 450. And this tank is not circular. It's an aquarium. They use 2 meters long, I'll make it 3 meters long. An aquarium 3 meters long, 1 meter wide, 1 meter deep, is full of water. Can you find the work needed to pump half of the water out of the aquarium? And I'll write that down. So when you have an aquarium, it's 3 meters long, 1 meter wide, 1 meter deep. 1 meter deep. Full of water. So we're going to find the work needed to pump half the water out of the aquarium. So we'll start by just drawing a picture of this. It's 3 meters long, 1 meter wide, 1 meter deep. All right. Like that. You want to make another trace, you can. This thing is 3 meters long, 1 meter wide, 1 meter deep. It's full of water. All right. So we want to find the work necessary to pump half the water out of the tank. So we're going to start out by just taking a slice out of here. One slice. How about the slice right here? Take one slice. Goes across. I always like to draw it again. It's like, well, what would this slice look like? It looks something like this. There's that one slice. It's 3 meters in length, right? It's 1 meter wide. But I'm using this delta x as its height, correct? All right, so I'm going to put a delta x here. And we'll talk about what's the force acting on this part. Take this out of the way. What is the force that acts on this right here? Well, I can start with, because it's water, everyone, this is in the metric with the meters, so I'm going to use 9,800 newtons. Multiply by the volume. What's the volume of that slice? Right there. And eventually, we'll just set up an integral and sum of infinite amount of slices. What's the volume of that slice? Last time we used pi r squared, right? This is just length with height.
This is 3 delta x.
I like it. 3 times 1 times delta x, or 3 delta x. I'll still put 3, 1, delta x, just so everyone knows that this had different dimensions, I would use it, right? Length with height. You just think of it as length with height. There we go. Okay, with the weight of water. So there's the force acting on that slice. But now, what's the distance? How far down was that slice involved? So if I scaled this as x equal to 0 here, and x equal to 1/2 here, and x equal to 1 here, right? Then what's the distance needed so that this slice gets pumped out the top? Because as they said in this problem, how much work is required to pump all the water out over, whoops. Find the work needed to pump half the water out of the aquarium, and they are talking about out the top. So, what distance can I use? How far down is that slice? Just distance x? Sound agree? Well, this would be a distance x, right? Just from that, just x equals 0. Excellent. So our distance down would be just distance x. So we have force times distance. So now, we're just going to do the summation of all these forces. We're like, hey man, just sum all these up. So I'll set up my integral and put all in this 9,800. Can I put any other numbers out front? The 3. The x, I'll put the x here. What do we put for the delta x? No, that's that. This I did put right there. Now, is it 0 to 1? If I do 0 to 1, how much water what did I actually calculate? All the water. Brilliant. So what should I do for my limits? 0 to 1/2? Does that make sense? Cool. I just wanted to make sure in the end you go 0 to 1. Yeah, they said pump all the water out of the tank. That's exactly what we do. Excellent.
So for the units from the end product, would it still be fixed out? Still would be-
Great question. In this case, because we have the newtons, and remember it was 98 newtons, and this was in meters, so it becomes Newton meters, but what do we call Newton meters? Starts with a J. Joules. And we'll just put a big J. You want to spell out joules, Joules, but most students just put a J. Just put a J for it. So let's find this, and we will put that joules at the end for the work necessary to pump half the water out of that tank. Everyone okay with this? So this is the key to working these problems. They're not that bad, but you do have to examine one slice. You just got to examine one slice and then say, okay, I'm just going to sum all these, and that's where the integral gets involved. And see how much you have to take out of there. Hey, what's the integral of x? X squared over 2. 0 to 1/2. A half squared is 1/4. But 1/4 over 2 is what? So 1/8. Alright, so this is what I'm getting. Carry that 900 down, carry that 3 down. You get 1/2 squared divided by 2, that's 1/8. 9,800 times 3 times 1/8. And it's just going to be, we're like, well, it's Newton meters, but we'll just write joules. J for joule. Somebody want to hit that? Please simplify that. 3675 Jen. Thank you. Thank you. That's the work necessary to take it out.
Do we need to put units on test?
Yeah, definitely use units. And when it comes to the work problems, just remember, if we're in the US customary units, it'll be the foot pounds when it comes to your final answer for work. And when anything in the metric system, just put down joules. What's that?
Don't use Newton.
I wouldn't take off if you did. It's funny, but yeah, it's funny when you get that, you're like, oh, that's just joules. But most of the time in terms of work, we will refer to it in joules. Doing a great job. Let's now examine two more scenarios. Okay, we had the circular cylinder. Now we had the rectangular prism. Let's look at when this thing is a trough, but it's something like this. Like a triangular trough or a triangular prism. Let's look at that. So that was like number 19, and this is like number 21. So some of you might have already tried this problem. I will just change the number slightly, just to give you extra practice. This tank is full of water. All right, so this one's full of water. I'll take this out of here. And we're going to find the work necessary to get all the water pumped out of the top. Well, this is like 21. All right, I got a triangle. I'm just going to change it a little bit, okay? They said from here to here is 3. I'm going to just say from here to here is 4. They said from here to here is 3. I'm just going to change that to a 4. They said from here to here is 3. All right. So when there's that triangle, 3 for this distance, 4 for the height there. But it's a trough. And it comes out like this. You want to draw another triangle, you can, you know. It's like they used 8 here. I use the same number. The units are meters. So this is 4 meters. This is going to be 3 meters. Oh, question.
No, my question.
Okay. So 8 meters for this, 3 meters up here, 4 meters here. Hey, the problem in the book just made this 3 meters. There's one more thing. There's a spout at the top. I'm going to pump the water out of that spout too. Comes up, and when it's extended, 2 meters. All right. I'm not drawing a scale, but that will do. This thing is full of water. This tank is full of water. We're going to find the work necessary to pump all the water out the top, out right there. Okay? Just like the last problem, but we will examine one slice. Sound good? But we'll get one slice. All right. I'll let Joel copy that. I know somebody's still drawing that picture. Okay. Why are you drawing it, everyone? I'm going to pick one slice, maybe have it right here. Take this thin slice. Hey, Art, how thin?
Turkey.
How thin is it?
Slice of turkey bread.
It's like a turkey. That's what we're saying. So thin, right? Infinitely thin. We make that what? Delta X height? Well, there it is. I'm not looking at it, but isn't that a rectangle? That slice. So I'm going to draw it again. Isn't it like before? Yeah. Okay. This is just like the last problem. This is just like the last problem. All right. So we're coming up to here. Here's a slice. How long is this? 8 meters. Great. What's the height? Delta X. Here's the challenge for this problem. I'm going to put force. Okay, I'm going to put a big long line. Let me remember, is this 9800 or 62.5? Because it it is involving water, right? So I'm gonna use 9,800. 9,800, you're gonna put 9,800. Okay, multiplied by length, width, and height, right? Length, width, and height, what's the force just acting on that one slice? Coming out of there, just like, let's look at that one slice. Man, this is pretty cool. Everyone, the height is changing, X, right? The length is 8. This is still 9,800. And here's our challenge. The W. That one I'm just going to put a sad face here. That's the only thing making this problem maybe slightly more challenging than the last problem. You all agree, look at all these slices in here. Aren't the widths changing? You all agree? Like, look at that slice, now look at that slice. Won't the width be different? That was different from the last problem, it was a lot easier. The width was constant, remember? So we got to do something. We got to come up with the expression for the width in terms of what variable? X. It's not too bad though. I don't want you to think it's too challenging. What I do, this is my recommendation, you don't have to do this, but this is the one time I actually will scale this from x equal to 0 at the bottom towards the top. Okay? I do that because I like to look where the point is. If I see a triangle, I go for the point. That's where I'll scale x equal to 0 from. And you go, why? I just do that because it's easy to deal with. We're going to deal with some similar triangles here to figure out what this variable x is. I just think it's easier. So what I do is this one from, if I put x equal to 0 here, x will equal what here? 4, and what will x equal here? 6. So I'm about to make a scale here. I'm just going to go x equals 0, x equals 4, x equals 6. Okay? X equals 0. X equals 4. X equals 6. My scale, I got it scaled. So and I just want you to know about similar triangles. They're not bad to deal with. Here's a big triangle. This is what? 4 from here to here. And this is 3 from here to here. Okay? And we're trying to figure out if we call this distance, I'll use the other chart. This distance, x, we got to come up with an expression for this right here, this width, w, in terms of x. And we can do it, everyone, by proportions. Because these are similar triangles. And all sides in similar triangles are in proportion with the corresponding sides. So I can set up a nice proportion. 3 is to the 4 as w is to the what? X. And I'm going to set up a nice proportion so that you and I can rewrite this w in terms of x. So it's not too bad. So what is w?
3x over 4.
3x over 4. That's what we're going to call the width. So I'm going to take this, put that right there. I can squeeze it in. All right, it's a happy face now because we figured out what the width is. This will represent the width throughout every slice, all the slices. Okay? Cool. Now, let me fit it in there. Right? So what's the width now? 3/4 x. What was the height again? Delta x. We've got 9,800, 8 for length, 3/4 x for the width, and delta x for the height. There's our force. Woohoo! Yeah, but what are we going to call the distance? Because Professor Messenger scaled this being x equal to 0 at the bottom, rather at the top. And we're pumping the water which way? Up there. Look how far you got to go. Up to there. So what will be the representation for distance?
6 minus x.
Man, you are good. Did you hear that? He said 6 minus x will be our distance for each slice. Just to make sure you understand why. Let's say the slice was right here at x equal to, no, I'll go lower. Let's say the slice was at x equal to 2. Plug a 2 in there. 6 minus 2 is what? 4. See how it would have to go a distance of 4 to go out that spout? That slice of water? As thin as a slice of turkey he's talking about. Right? And what if the slice was down here at x equal to 1? Down here, you got a slice down here. You plug a 1 in there, 6 minus 1 is what? 5, we're saying, oh yeah, that slice of water, you get pumped up to this location right here, would be a distance of 5 meters, right? Cool. How about the slice that's right here? And x equal to 4. Now you plug a 4 in there, 6 minus 4 is what? Distance 2 off the top. Cool. So far so good? So we just wrote it as 6 minus x, because I feel x equals 0 on the bottom. Everyone, all I'm going to do is slap an integral symbol on all of this, change delta x to what? Dx. But you got to help me with the limits of integration. I do want to emphasize, this tank was full of what? So it's like, where's the water? That's where you're going to fill your integral symbols. That's where your water is. Look carefully, because when you set up your limits of integration, I want you to set it too high. That's where the water is, right? Here, let me show you all. Full of water now. Set this up, 9,800, I can put that in front of the integral, right? Any constant, the 8, the 3/4. Any other constants? Nope. Now I'm going to put the integral symbol. You got what variable? X, make sure you don't miss anything. You also got the 6 minus x. This becomes the what? Dx. Dx. Now, 0 to, brilliant. Did you hear how loud that was? That was good. They didn't say 0 to 6. Some of you may in class may think it's 0 to 6. They said 0 to 4. They said the water is only located from what? Look at our scale. That's where the water is. So that was just a very thin pipe. The spike came, the water came out of that little spout in there. You go, what? Did we take care of this? Yeah, we took care of it right there. We took care of it right there. So that's why it's accounted for. When you told me that the distance it had to go 6 minus x, you took care of how far that had to go. Cool. Hey, just so no one's confused, if this wasn't here and the water was just coming out of the top here, the only difference would be, this wouldn't be 6 minus x, what would it be? 4 minus x. You got it. And that's just me, I like to, when it comes to these shapes like this, I look where that point is, and that's where I'll scale x equal to 0 from, because I think it's easy to set up to similar triangles and do a proportion, set up a proportion to see what that width is going to be in terms of x. Cool? Awesome. Hey, you don't have to solve this now. The answer would be in what? Joules. But if you did have to do this integral, you could distribute that, right? 6x minus x squared, and then multiply all that. Unless, did someone want me to solve all this? I'll be glad to. I'll just say, you got the 9,800 times the 8. See, the setup's the most important. I know you all can integrate this. That's just the integral of what? 6x minus x squared. We don't need a u sub or anything. True? Maybe later today we'll need a u sub. What's the integral of that? 6x squared over 2, that's what? You go from 0 to 4, and you can multiply all these 9,800. 3/4. Plug a 4 in there, and then we'll put joules. Hey, if you don't mind, would 2 people do that? Just so we have someone to verify that the other person did it the same way.
1,568,000.
1,568,000. We'll see if anybody else gets it. 1,568,000. Oh, you're the best. Sean, thanks. I wrote 8, I wrote 8, I wrote 8. I must have looked at that and thought it was a what? My sloppy handwriting. That's an 8. Did you use an 8? I apologize. Oh, cool, thanks. You got 1,568,000, right? Anybody else get that? That's it. 1,568,000 joules. Not bad. Hey, one more of these problems with the tanks. I want to do one like number 22. What if the tank is spherical? This is the one I want to do last. Not that it's crazy hard. It's just, we're going to scale this from a specific location. So far, where have I scaled everything? mean, from ropes to what, tanks? I usually scaled it from the top. Things were getting either pumped out of the top, the rope was getting lifted up toward the top of the roof. This was the only time I thought I'll scale x equals 0 here because I thought it was easier to deal with this, right? Well, this time, everyone, it's going to be a spherical tank. It's spherical. Has a little spout at the top. I'll draw it. With spheres, the nature of a sphere, it's what? Where is it widest? In the center. That's where I'm going to scale it. So when it comes to spheres, you'll find that it's easiest to scale those. Only that one. Only the sphere from the center. So I'm going to draw that. Does anyone copy this? So I'm going to draw this sphere like 22. Actually, you know what? 22 is even. The answer's not in the back book. I'm going to use the same numbers. Hit change raise. I'm going to use the same numbers. There you go. Here's some sphere. When it's got a little spout at the top, the radius is 3 meters. The radius is 3 meters of the spherical tank. It's full of water. All right. There's a little spout at the top, 1 meter. What? 1 meter. Full of water. Find the work necessary to pump all the water out that. Well, only the sphere. I'm going to scale from the center. X equals 0. Okay. Let me go up with just a vertical line. Right there, x would equal 3 right before the spout. Does everyone agree? And then I add the spout 1 meter and get up to what? 4 meters. So far, so good. X equals 0. X equals 3. Let me make sure that's lined up. There we go. Yep. X equals 3 right there. X equals 4 at the top. And what am I going to do down here? This is like a y-axis. We can call these y's if you want. I'm using x right now. Feel free to use the variable y if you think it's easier. But, and this would equal x equal to -1. X equal to -2, and what would this be? X equal to -3. So feel free to label this. -3, -2, -1. These would be negative values. Because I scaled it, x equals 0 from the center. 1, 2, 3, 4. Then these would be negative. Good. But look at that slice. Isn't it a circle? Right? We'll get these circular cylinders again. Does anybody know the relationship in a circle back in just the xy plane with a radius of 3? You know it's something like this? Do you know that's the equation of a circle with a radius of 3? So when we have to come up with a representation for the radius, is that when all these slices, isn't the radii changing? Yeah. Isn't the radii changing in all these slices? We keep pulling out slices, the infinite amount of slices, yeah, they just keep changing. We're going to call the height, what, delta x? But every radius won't be 3 meters, true? So to find a formula, an equation to represent that radius, we can definitely use this. Okay? But I either solve for x or solve for y. If you solve for y here, what would the equation become? Right? It comes out, but what would y equal? Square root of. Now in this case, this is the equation of a circle in the xy plane with the radius of 3. Okay, yes sir?
So if the radius was like 2, what would be the equation?
Great question. It's always x squared plus y squared equals r squared.
Oh, okay.
So if the radius was 2, you would put what here? 4. I love your question too. And what if the radius of the sphere was 5?
25.
X squared plus y squared equals 25.
Cool.
Excellent. And when this is going to be the representation of our radius. This will represent a radius of each slice. You can check it. You want to check it? Let's plug in. What's x equal to right here? Let's just check it. Let's make sure this is the equation of the radii for all the slices throughout our image. Wasn't too bad. What's going on at x equal to 0? Plug a 0 in here. What's the square root of 9? Square root of 9 minus 0 at c, the radius is 3. Now try this. Go up here to x equals 3. and the left. Now, think about the slice right there. I know a lot of you are looking there going, there is no slice. Well, try it. 9 minus 3 squared is what? 0. The radius is 0, left and left, right? But if you look right here, what's actually equal right there? Like x equals 2? Okay, 9 minus 2 squared, 9 minus 4, the radius would be the square root of 5. But there you go, you got a representation. Now go down to these negative values. I didn't want you to think that these negative values were going to interrupt our math problem. Go down to like right there. What's that slice going to be for that cookie that we pull out? You plug in negative 2, what's negative 2 squared? 4. What's 9 minus 4? Square root of 5, that'll be the radius. Cool. So when this is cool, this will represent our radius in our equation. But, like the other problems, I'm going to pull out a slice and let's look at the force carefully. Meters, am I going to use 62.5 or 9800 because there's water in this thing? Yeah, we're using 9800. So here we go, what's the force? Well, let me take a slice. I can take that slice right there. Look at this one. It is circular, so it's like this. I want to pull it out. Let's look at that. Right? It's got a very so thin. The height is delta x, right? Do you remember the formula for volume? So we're going to do 9,800 newtons times the volume of that slice. And when it's pi r squared times the height, right? So let me write this again. You got the 9,800. The pi, 7 degree pi r squared h is the volume of that slice. What are we calling the radius again? The square root of 9 minus x squared squared. And what are we calling the height? Delta x, delta x. Now, and there's your force. You got 9,800 times the volume. That's the force acting on that one slice. Now we need distance. All right. I'm going to need some help with the distance. So there we go. I'm going to stick that in an integral. The distance. Can you help me with this? Because when I didn't scale x equal to 0 here. So it's definitely going to involve that subtraction again, isn't it? Golly. Should I do x minus 4 or x minus 7? And we'll check it to make sure it works. All right? What do you all think? What should I use for my representation for the distance of each slice getting, you know, if water's just going to get pumped out of the top, we're thinking of each separate slice. Wouldn't it be the 4? Let's check it out. You know, before we did what? X minus, we did 4 minus x or 10 minus x. Let's look at this. If I use, in this case, let's say it was, so we're trying to think, I want to try to use 4 minus x